we're going to start from a start node. We're going to start from a start node. And we're going to explore paths from the start node. We're going to think about that, and we're going to start exploring paths. And we're going to explore paths in some ways. And here we've got this frontier of nodes here that we're considering. So that's what we're going to do. So here we have this set of things that we're exploring. A frontier of paths from the start node. We've explored this arc, this arc, this arc. We've explored all of these paths. And what happens is the algorithm is pretty simple. It's just going to expand the frontier. So it's just going to expand this frontier into places that we haven't explored before. And the way that we expand this frontier is called a search strategy. We're going to explore a number of different search strategies. A lot of them are actually going to try to use as much extra information as we have, as well as the graph. So here is this. All right. So here's the algorithm. Here we have a start node. We have all of these explored nodes, and we have the paths at the ends of the paths on the frontier. We have the set of nodes, and we have an unexplored nodes out here. And the idea is we're going to just expand the frontier into new nodes at each time. And when we hit a goal node, we're going to have found a path. So that's this algorithm is sort of reasonably simple at an abstract level. Okay, so here is this. So here's the graph. So here's our pseudocode. We're going to input a graph. We've got an inputting a start node, set of start nodes, a Boolean procedure. This goal node to test if something is a goal node. We're going to start off with all of the start nodes. And we're going to keep going while the frontier is not empty. We're going to keep removing a path. So this frontier is a set of paths. We're going to, while it's not empty, we're going to remove a path from the frontier. If nk is a goal node, we're going to return the path. So we found a path. Otherwise, for every neighbor, of the end of the path, we're just going to add an extra node to it. Okay, so in here, it's sort of reasonably straight. If I have a simple graph that looks like A, B, C, D, E, F, G. Right, I can start off with just the start node here. The start node could be A. So it's just the path with just has one node in it. I'm going to remove the front. This is the frontier. While it's not empty, I'm going to remove a path from it, which is this. It's not suppose this is the only goal node. Whoops, suppose this is the goal node. I'm going to start with the frontier as just a single node. I'm going to remove a path from it. There's only one path from it. It's not a goal node, so I'm going to, for every neighbor, I'm going to add the other pairs to it. So it's going to be A, B, and A, C. So that's the frontier has now got this. I'm going to select one of these. You know what? Let's select one of them. Let's select this one. So I've got AC. I'm going to select, let's underline this. I'm going to select this one. I'm going to look at the end of the node. B is not a goal. So for every neighbor of B, which is just D and E, I'm going to add that elements to the frontier. So then I'm going to have A, B, D, A, B, E, and A, C. And I'm going to select and remove one more of these. I could select this one. I can select A, B, D. And now I'm going to see, is D a goal node? No. I'm going to add all its neighbors. It doesn't have any neighbors. So then I'm going to end up with the frontier that looks like A, B, E, and A, C. And maybe now I'm good. All right. And now we're going to select one of these two. Let's suppose we select AC. And now we're going to say, is C a goal node? No, we're going to add in all its neighbors, and its neighbors are F and G, so it's A, B, E, A, B, E, A, C, F, and A, C, G. And now I'm going to select one of them. Let's select this one for some unknown reason. F's not a goal node, so I'm going to add all its neighbors to this frontier, and it has no neighbors, so I'm going to just, so for every neighbor I'm going to add this, but there aren't any neighbors, so I'm not going to add anything. I'm going to get to A, B, E, and A, C, G. Let's select this, and I notice that when I select this, G is a goal node. So that's the I'm going to return. So here I'm going to return A, C, G. Okay, yeah.
This algorithm seems to assume we don't really have loops, like we can't get back to the same state, but it seemed like in our robot game you could. So I guess I'm wondering, is that just something we're doing when we set up our graph? We just make sure we don't put arrows?
No, we're allowing loops. This actually allows for loops. So what's going to happen? So the story is, how you select this node is going to give you the search strategy. So we're going to look at a number of different search strategies. And then we're going to look at ways to get rid of loops. And in particular, we're going to look at actually detecting loops. And the other one is to make sure we aren't searching multiple paths to the node. And they have different trade-offs according to how much space you need and how much time it takes. So we're going to talk about search strategies. We're going to talk about how to select nodes from there. We're going to talk about what to do when you have multiple paths to a node and when you have loops. We'll have to solve that. And we're also going to talk about how to use extra information about what you know about a graph. So a classic sort of pathfinding algorithm can be Dijkstra's algorithm. But Google Maps doesn't use that because it actually knows a whole lot more information about maps than Dijkstra's algorithm assumes. And we're going to talk about how to incorporate lots more information about things. So we'll get to this. So this is just a very basic one that we're going to elaborate. It's a very sort of simple algorithm we're going to elaborate as we go on in the next week or so. All right, let's stop here. Please hand in your assignment 0 down here.